When we exceed the capabilities of ARC Specialties, we call in the big guns. Today we're at Stress Engineering where they have the big testing machines. I'm here with Sarah Henson with Stress Engineering. So we tried to blow this additive sphere up at ARC Specialties with 5,000 PSI and we failed. Sarah called me. What's your limit here?
We've got 60,000 PSI available in this test setup.
So there's no doubt we're going to rupture this sphere.
Ideally, yes.
So we're going to have video of it being pressurized and the whole failure?
Yes.
This is not your first additive job, is it?
No.
That's something you guys test routinely.
We do. It's very exciting, and especially when you get to this part and get to blow things up. That's always the best part of the test.
And you and I realize this is just dramatic. It's fun. It's just to show that additive is real. But how do you actually test additive parts?
You can start with the materials and material characterization. You could do that through basic mechanicals. There's codes that outline all of your requirements there, corrosion testing, and we've got the ability to do full-scale bend testing, fatigue testing, tension testing, anything that you want to do to check it out at a large scale as well as subsize.
And what's experience? Is all additive good? Is all additive bad?
So far, so great.
Yeah, the reality is you still have to make a sound weld to make a sound part.
Yes, sir.
Okay. And so we're going to pressurize this and just take it to failure.
Yes.
Okay, so can we go over there and watch it on the screen as we do this?
Yes, absolutely. Let's go.
Let's go.
This video is from inside the test bunker at Stress Engineering. What we have is an 8-inch sphere that we made with additive manufacturing. We use a 316L material, which should have about a 75 KSI tensile strength. So somewhere around 4,000 PSI internal pressure, we should see failure. But today we're going all the way to 6,300 PSI. What that means is we have over 300,000 pounds of force trying to separate the two hemispheres. Finally, at 6,200 PSI internal pressure, we developed a leak. That's a good thing. On a pressure vessel, you want to leak before rupture. So when our sphere finally failed at 6,200 PSI internal pressure, the tensile load on the wall of our vessel was 100,000 PSI. This is 36% higher than you would expect from 316L material. And you can see in the two pictures before and during the pressurization, this entire sphere expanded like a metal balloon. The point of the exercise today was to demonstrate that additive manufacturing will allow you to produce parts which are hard to make using other technologies, and you can achieve material properties which meet or exceed normal standards. If you think you might have a part that would benefit from additive manufacturing, give us a call. ARC Specialties thrives on problems. Send us yours.